Now this is big slide actually, whatever I made, but I'll be giving only some overview here. Okay, what is this question? Charge distribution inside a material of conductivity sigma. Material of conductivity means is a conductor. Okay, speak up. Permittivity epsilon. I mean, need not be conductor. Ohmic material. Okay, speak up. Conductivity sigma, permittivity epsilon at initial time equal to rho of r comma 0, isn't it? Speak up. That's equal to rho naught. Okay, at subsequent time. Speak up. From continuity equation, we derived this one. Am I right? Rho of t is equal to rho at time t equal to 0 e power minus sigma by epsilon into t. Am I right? Very direct question. 5 marks question in CSIR actually. Okay, speak up. This has a similar question. Suppose that free, I mean, whatever I suggested, the problems or theory from Griffiths, okay, questions are there. Okay, very dominant questions are there. Suppose that free charges are, I mean, if you haven't done that one, you have to do. That's what I'm saying. This is in the electromagnetic waves chapter. Am I right? This one, this derivation, I don't know. Maybe in the electromagnetic waves or yeah, electromagnetic waves chapter inside a conductor in that region, I think. Okay, speak up. So from this one only we define good conductor and bad conductor. One problem remained, one gate problem remained actually on this one. Okay, speak up. Suppose that free charges are present in a material of dielectric constant epsilon equal to 10 and resistivity. If your resistivity given, conductivity can be found. Am I right? Pick up 10 raised to minus 11 per ohm per meter. Am I right? Per ohm per meter, isn't it? Speak up. Using Ohm's law, the equation of continuity. I mean, look at here. He said using Ohm's law and equation of continuity. He said that one. I mean, we derive this one using Ohm's law and equation of continuity only. Speak up. Just recall that one. Uh, the time required for charge density inside the material to decay 1 by E. Rho of T is equal to, speak up, rho naught. This rho is charge density. This rho is resistivity. Bit confusing terminologies. E power minus sigma by epsilon into T. Am I right? Speak up. So at T is equal to epsilon by sigma. Am I right? That's equal to rho naught by E. Pick up. That time that you are looking at, that's equal to epsilon by sigma. What is epsilon by sigma? 10 divided by sigma 10 raised to minus 11, 10 raised to 12. Speak up. Second, in terms of second, everything in SI unit. Is that okay? Very simple question. This one, okay? Exponential decay. At what time it will be 1 by E of its original value? At that time is equal to reciprocal of this factor. Then it will be 1 by E, isn't it? Speak up. Very simple. Now look at here. I mean, I'm saying, suppose if you miss anything, that's why I took this question. Otherwise, I wanted to get into that radiation chapter. A circular loop made up of thin wire has a radius of 2 centimeter and resistance 2 ohm. It is placed perpendicular to uniform magnetic field. Okay, magnetic field is uniform, but it is time varying. Uniform means with respect to space. I mean, changing means with respect to time usually. Is that okay? Speak up. He said it is a uniform magnetic field. Okay. You have a circular loop of wire of radius is given. Okay. And resistance is given. The resistance is equal to, I'll write 2 ohm. Okay. Radius of the wire is equal to, pick up 2 centimeter. Pick up. Place it perpendicular to uniform magnetic field is in this direction, but it is time varying. He has given. Look at here. B is equal to B naught into, pick up, e power minus t by t naught, isn't it? Pick up. Uh, the field start decaying at t naught equal to 1 second. The field start decaying until 1 second. It was constant. It start decaying. Okay. Until 1 second, it is B naught. That's equal to 0.01 Tesla. Okay. Total charge that pass through a cross section of the wire during the decay is Q. Speak up. Wait. I read wrong. Okay. Field start decaying as where T naught is equal to 1 second. He has given T naught value. Okay. This value. It's not like that. Okay. Speak up. The total charge that passed through a cross section of the wire during the decay is Q. Okay. Value of the Q is. I mean, look at here. So when you wait for sufficient time, I mean, it will decay to zero, am I right? Magnetic field will decay to zero. Okay, speak up. The total charge that passes through a cross section of the wire, cross section of current will flow, am I right? Because of time varying magnetic field, you have induced EMF and all. Okay, speak up. During the charge is Q. I mean, this is very simple. Look at here. What is this one? EMF is equal to d phi by dt. Okay, speak up. D by dt of magnetic field into phi r square simply. Why? Magnetic field is perpendicular to surface. Am I right? Speak up. This is the wire. Okay, speak up. This is the wire. So suppose take copper wire here. Hmm? Magnetic flux linked with this one is this one. Is that okay? Speak up. Now this side, I think this kind of problem is there in Griffiths. Okay, speak up. This side you have I into radius, radius into I. Hmm? Radius into I. Speak up. Current. Sorry, not radius. Resistance into current. Speak up. Hmm? Yeah. So pi r square, r is small r is a radius. What is this one? A b naught outside. Am I right? D by dt of e power minus t by t naught. Keep it as it is. Keep it as it is. Don't differentiate. Don't differentiate. I mean, here comes the main. There is similar problem in Griffiths. Okay, speak up. Negative sign have not much role here. Okay, I mean, we didn't take that negative sign. We use what you call your Langella to find the current direction, isn't it? Okay, so and I need only magnitude here. Okay, speak up. Actually, yeah. Now look at here. R I will take it here. Current, can I write it as dq by dt? Hmm? Or d small q by dt? Hmm? D small q by dt, that's equal to pi r square. Small r is the radius, capital R is the resistance. Okay, speak up. So B naught into, speak up, d by dt of, okay, e power minus t by t naught. Okay, speak up. Now what I do is I'll multiply everything. dq is equal to, speak up. So pi r square by r, the total charge, can I say 0 to q, total charge which passes, I mean, through a cross section or whatever you can take. Okay, this q is the total charge. Okay, speak up. Pi r square b naught into d e power minus t by t naught divided by dt into dt, integration from 0 to infinity actually. Why? I mean, that is decaying exponentially with respect to time, isn't it? I mean, this expression, I mean, we didn't use in this way actually. Hmm? In one Griffiths problem, he asked what is the total charge which goes around the circuit. Okay, in one of the problem, there he cancelled out this denominator part. He find total change in flux, total change in charge or something. He cancelled out this dt part. Okay, but I'm doing it like an integration here. Is that okay? Pick up now total charge. That's what he's asking. Am I right? Pick up the value of q in microsecond, microcoulomb. Okay, round off to 2 decimal places. Is that okay? Speak up. Hmm? Now this is equal to q, that's equal to pi r square by r b naught. Derivative, the integral of differentiation is e power minus t by t naught, or 0 to infinity. Hmm? Pi r square by r b naught, upper limit 0 minus 1. Oh, it's not required at all. Hmm? That T naught is not came into play, am I right? Check this out. T naught didn't appear there. Hmm? I think I need. Yeah, can you quickly? So tell me the answer. I mean, radius equal to 5 into 2 centimeter square. R is 2 ohm into B naught, some 0.01 Tesla. Okay. Speak up. I think I better give the hints only, otherwise we can't touch more problem. 0.01. Now, if you have taken negative sign, you would not have end up with negative sign. So can you do this one quickly? Speak up. Convert it into meter. Pi. Not multiplied with anything. 2 pi. 2 square. Yeah. 2 pi means 6 point something. Yeah, that's right. Okay. Do it carefully. Do it carefully. I mean, this problem, what he has given is, I think he has taken one solenoid. Am I right? Do you remember that problem? Okay, there he has taken one wire with which is covering that solenoid. He take that solenoid to infinity, or he take the solenoid and insert from the other side back. Then what is the total charge which is flown through that one? Okay, there the same question. What is the total charge flown through that one? Okay, so there, if you take this solenoid and if you throw out to infinity, initially you had some flux, finally you have zero flux. You can find change in flux. Actually, you can do like this: delta phi divided by delta t, that's equal to resistance of the I mean EMF into delta q divided by delta t. You can write like this: delta flux of magnetic field. There, what he did, he cancelled out this one, and change in flux. Change in flux is nothing but initial flux. Got my point? Okay. So that's equal to total amount of charge flown. That's how we argued. There also you could have done integration actually. Speak up. See that problem. That's why, next, until exam, you better to, whenever you face any difficulty, you go and solve Griffith's problem. It will be sufficient. Okay, speak up. Two rails of railroad. This is very frequent question in just exam. That motional EMF first problem we solved. Am I right? We had one register and we had one track. One rod is moving. Isn't it? Pick up that kind of problem. Actually, okay. Two rail road track are insulated from each other from the ground and are connected by a millivoltmeter. What is the reading in the millivoltmeter when the train travels at the speed of 90 km per hour down the track? Assume that vertical component of the earth magnetic field is 0.2 Gauss. Okay, magnetic field is given as 0.2. It is CGS unit. Okay, speak up. He has given 1 Gauss is equal to 10 raised to, you can write 0.2 into 10 to the power minus 4 Tesla. Am I right? Speak up. Now, what is asking, assume that vertical component of the earth magnetic field is 0.2 Gauss and the tracks are separated by 2 meters. Okay. What is asking? What is the reading in the millivoltmeter? That is EMF itself is a reading in the millivoltmeter. Okay, speak up. You have to find, EMF is equal to, I think, BLV, as I remember. We use that one many times. Am I right? Pick up. Check that out. Can you do this one? Speak up. I'll move on. Okay. Lot of slides are there. Okay. And there is one more question here. Okay. On the same thing. Look at here. Just question on railroad or something. Okay. Point to the same question. Repeat it twice. Okay. In just exam, one or two question will be very repeated, directly repeated. Okay. Now look at it. This also Griffith's question. It was there in last CSIR net exam also. Last CSIR net. Okay. Two conductors are embedded in the materials of two conductors. Okay, arbitrarily. Okay, so they are embedded in a material. Speak up. It is embedded in a material of conductivity 10 raised to like that. Okay, speak up. So I'll not take this one. I need a what you call to apply Gauss law actually. Okay, here you have your conducting material. Okay, speak up. I'll just put these two are our conductors. Okay, speak up. This is one conductor. This is another conductor. Is that okay? Speak up. So it has a dielectric constant 80 into I think epsilon naught should happen. I hope so. Okay, speak up. material of conductivity. Can I write sigma is equal to 10 to the power minus 4 ohm meter? Ohm meter is the, okay. So dielectric constant epsilon is equal to 80 epsilon naught, I hope. Okay, I hope so. Okay. The resistance between the two conductors is 10 resistance is given between these two. I mean, there is a ohmic material. These two perfect conductors are embedded. Can you recall this problem? Speaker. 7th chapter. Am I right? Problem 7.3. Problem 7.3. Okay, speaker. What is the capacitance between these two conductors? Okay, ignore the decimal part of the answer, whatever. Okay, look at here. I'm doing only the what you call numerical part. You have to practice up. Okay, you didn't do that one. Next 10 days, concentrate on it one while doing the practice test. Okay, while writing those numericals and doing the calculations and all. Okay, now what we do here is uh, capacitance. I mean resistance is given. Am I right? 10 raised to 6 ohm. Okay. As I remember, the approach was like this. Okay, we take one Gaussian surface around one of them. Okay, what we need to basically do is, okay, you need to do current. Am I right? You need to find current flowing from one to other, one conductor to other conductor. That current is nothing but integral of j bar dot dA bar. Now, while finding that current may be flowing in any manner, like this, okay, like this. Am I right? Because these are all conducting. Ohmic material actually. This is conductor. This is ohmic material around that one. So that's why, since that current can be what you call flowing in any, charges can be flowing any manner. While finding this current, okay, what I will do is I will completely enclose one of the conductor. Or suppose you say this is a positive plate, positively charged conductor, this is negatively charged conductor. Charges are flowing from this one to this one. So to cover all charges, I will take one closer surface. Closer surface. Is that okay? Speak up. In the next step, what we have to do is using, where you have applied this surface, where you are defining this J vector in this ohmic material region. Am I right? On the surface, you have defined this vector field on the surface actually. On the surface, J is equal to sigma into electric field. Sigma is the conductivity of this ohmic material he has given. Speak up. Do this problem again if you are not getting that one. When you substitute this one, then current will be, it will become Gauss law. I is equal to, speak up, closed integral of, speak up, E bar dot dA bar. Isn't it? It will become Gauss law. That is equal to how to connect it to capacitor. We have assumed two charges. He didn't mention that one actually. So plus Q suppose here, minus Q suppose here. So that's why this is equal to sigma into Q by epsilon. Is that okay? Speak up. Now again, capacitance is nothing but I into R is nothing but voltage. Speak up. Potential difference between them is nothing but I into R. Speak up. I into R. That's equal to R sigma Q by epsilon. Okay. So if you know potential difference, you can, if you know the charge on the each conductor for any geometrical configuration, how do you write? Q is equal to CV Q by C V. Okay. Speak up. That's why what I will do here is this is equal to Q by C. Potential difference is equal to Q by C. When you see this one, what is C? Epsilon by R sigma. Speak up. That's right. Epsilon by R sigma. But he has said, I think, epsilon is equal to some 80 epsilon naught divided by R sigma. Okay, that is the problem. You just have to substitute those quantities. Isn't it? Just have to substitute those quantities. Dielectric constant epsilon is equal to 80 epsilon. Just I will just check the question. But I hope you got this one. Okay. The same question, exactly the same question is asked in last CSR net exam. Okay. I mean, you start assuming. I mean, there are charges on them. Okay. Speak up. I mean, that means you maintain some what you call potential difference. Okay. Speak up. There exists a charge on them. Start defining current. Okay. Speak up. After that, that will become what you call since that is closure surface. We didn't had closure surface integral here while finding the current, because we used to take wires and all on cross sectional part we used to take. But here it happens to be if you are not taking closed, you may lose some charges. It may move like this, who knows? Okay, because this whole thing is ohmic material, isn't it? Speak up. So that's why after that, what you call Gauss law. Okay, so then current into, he said he has given the resistance of this configuration. Okay, speak up. So current into R is nothing but potential difference between them. Potential difference is equal to Q by C. Now this relation ultimately gives us what is the capacitance of this geometrical configuration. Okay, so they asked part B of the question. Okay, I mean how what you call, if suppose if we fully charge and if we leave that one, how it will decay? It will decay like V is equal to V naught e power minus T by RC and all. Am I right? See the capacitance that we now here. They asked the part B of the question. Okay, note on this question. Okay, I mean all questions are there. Okay, I think in the assignment. Am I right? Only potentials and fields and radiation assignment I didn't put up. All other assignment up to this chapter I put up. Okay. Again, this is the same question. I'll move on. Consider a sphere of radius r containing charge, volume, charge density. The charge is 0 outside the sphere. Electromagnetic potential inside the sphere may be written in many ways. Which of the following gives that? And I think from this one you better to find electric field. Okay. From this one, find electric field. Use Gauss law. Divergence of the electric field. Cross check with whether you get this one or not. Speak up. So shall I move on? Speak up. Charge is 0 outside the sphere. Okay. Speak up. Charge is 0 outside the sphere. The electromagnetic potential inside the sphere may be written in many ways. Okay. Speak up. I mean, I think we have taken one example. Am I right? I mean, for a charge which is at rest at the origin, you can make what you call your scalar potential 0. You can make vector potential be time dependent and you can define. Am I right? That Griffith's problem. Very similar to that one. Okay, speak up.